Hello. So we all care about performance, keeping our pages fast, making sure that we're using just the right amount of memory. How many people here have used the Chrome DevTools before to try figuring out if they have a memory leak in their app? How many people here have enjoyed that experience? Right, just like one person. Get out. No, so like I've been working with the DevTools for a few years. Memory profiling using our memory tools, they're fantastic, but at times they feel a little bit of a black box. And so in this talk, we're going to look a little bit at understanding how memory profiling works in the DevTools, give you some pro tips on that stuff. We're also going to do a deep dive into some V8 specifics to help you understand how things like the memory graph work. It's hopefully going to be interesting, but yeah. Whenever I'm building an app that I think is going pretty well, and I'm pretty happy with the performance, half the time I end up in this situation where I've got like this really nice smooth performance, and then someone just comes in and crashes into that nice feeling with like a plastic tractor. That is what a memory leak feels like to me half the time. So I've been getting a few emails from some friends that had a few memory profiling issues. And so what we're going to do is we're going to take a look at some of those emails and try to figure out how to solve these issues. So let's go and open up the DevTools on this page. Now, what's the first issue? So Paul writes in saying, why is my memory usage growing? My app slows down when I click on this button. Why is that happening? So the first thing you can do, before we actually go and open up the DevTools, the first thing you can do if you think that you have some sort of issue to do with memory in Chrome is actually go and open up the Task Manager. So the Task Manager is actually hidden in the Tools menu. So you can go to Tools and Task Manager. And what this will do is actually give you like a list of all of the currently open tabs and extensions that you have. And it'll list right next to them the current memory usage, CPU usage. You can actually go, and if you right-click on the top here, you can also expand it to show like the GPU memory, JavaScript memory, shared memory being used. And this is useful for just like getting sort of a hint about whether you've got growing memory in a tab. So in this case, we could go and try to find the Mail tab. If I go and I click on this button, I might have to drag this window a tiny bit. What I'll see is that, yep, so memory usage is growing in this tab at the moment. That's sort of useful for a very simple hint. But what I want is some more specifics. So what I'm going to do is I'm going to open up the DevTools, head on over to the timeline, and I'm now in memory view. This is, well, technically speaking, this is frames view and memory view. Just make sure you've got the capture memory option on when you're trying to work on this stuff. So memory view is really useful. If you haven't used it before, it's great for sort of tracking the total number of objects allocated in memory, seeing whether they've grown, looking at the total number of DOM nodes that have been allocated, how many documents have been created, event listeners allocated. So here I've clicked on my button, and if I go and look here, I can see that the memory usage in this page is growing. It's not growing too much, it's growing a little bit, but I can actually go and slice down this data, try to see what's going on a particular segment. In the bottom view where you see the memory pane, you can take a look at the size of the JavaScript heap, whether that's growing, again, the documents, the nodes. Right off the back of that, we've actually got another question that was sent in. Where does GC, so where does garbage collection fit in with memory profiling? I'm trying to look at the time spent by the GC. Now, what I'm going to do is I'm going to click on Start Creating Chunks and go and start recording. And I'm going to explain a workflow for sort of tracking down if you've got a memory issue. So normally, if you think that you have a leak after you've taken a look at the Task Manager, try to identify like a sequence of actions that you think might be leading to that leak. So maybe it's like clicking on a button that's going to show more images in a carousel, or clicking on a button that's going to display more content in your page. So identify the sequence of actions that's suspected of leaking. Go and record a timeline like we're doing right now. And then the next thing you want to do, and this is pretty important, is use the trash icon. So there's a trash icon here that says collect garbage. And what this is going to do is basically force GC. If you don't click this icon, what's going to happen is that the objects that you have in memory are going to stay alive until the next round of GC. It's not a massive deal, but it just means that you're going to be waiting a while before you're going to be able to get a proper profile of this. Now, if you iterate a few times and you see a sawtooth curve, It might mean that you're allocating a lot of sort of short-lived objects. So what I mean by what I mean by a sawtooth curve is something that looks a little bit like this. So pay attention to what's in the red rectangle at the very top. So that's a sawtooth curve. If you see something that looks a little bit like this, it means you're allocating lots of short-life objects. And if that sequence isn't expected to retain memory, so if you're not doing anything too intensive, and your DOM node count isn't actually dropping, it might be an indication that you're leaking. So keep that in mind. Let's take a look at the next question we have. So we've got another question in here. This one's from Jake Archibald. So Addy, buddy, pal, I'm letting you find and fix a memory leak in my app. Also, please send a PR with the fix to my repo. Thanks, Jake. Right, so we just learned about how to go and try to memory profile something. Now what we've got here is what looks like we've got some tabs, and we actually have like a slider that's just displaying some images. I think this is like a carousel, right? So it's displaying different images based on the seasons. We've got one for autumn, summer, winter, and spring. Nothing overly complex. Now what we're going to do here is Jake thinks that he has a memory leak in his app. I'm actually going to reload the page in case any of the objects from our other examples are still hanging around. I'm going to clear that. And what we're going to do here is we're actually going to go and use the object allocation tracker in DevTools to figure out if we have a memory leak. Now the object allocation tracker, let's actually go and record this. So I'm just going to click on Start here. Start interacting. Now the object allocation tracker basically takes heap snapshots periodically throughout a recording. The bars that you're seeing here, the blue bars, basically mean new objects, and the height of these objects basically correspond to the size of the objects. So if something is getting sort of turned into gray, it means that we don't have to worry about it anymore. If it's staying blue, we do. So I'm just going to stop just there, and let's try narrowing down one of the thicker bars and see what's going on here. So I'm going to select a segment, maybe a larger segment than we've got at the moment. Let's take a look here. We've got DOM token list, we've got attributes, a node map. Let's try to expand it to the whole set. And what I see here is that I've got HTML li element, so a list element. That may be causing trouble. So basically, if how many people here have used the Heap Snapshot tools before? Small number of people, okay. Basically, what the object allocation tracker is doing in the background is it's taking a bunch of different snapshots, and it's basically leaving behind stuff that hasn't been correctly cleaned up. So here what we can see is that we have a number of different list elements, and if I go and I dive down into here, what you'll see in the retaining view at the very bottom is we've got a few different objects. We've got HTML document, details element, HTML div element. And what I see here is a reference to a variable name called last div. And if I actually hover over this, I can scroll down in this information bar and see that the inner HTML actually seems to be some of the content for one of these carousel items. Now, if I go over into my sources view and we actually go and take a look at the source for this particular example, I'm going to try bumping up the font size a little bit just so people can see it. Let's actually run through like the functions that are called here. So whenever I go and select a tab, it's calling this function called select tab, which is then going and calling load content. Let's scroll down to load content. We can see that it's doing two things. It's calling prepare content, which happens to be referencing last div, so maybe that's leaking. And it's also calling prepare gallery. Now, if we scroll down a little bit further and we take a look at prepare gallery, let's take a look at what's going on here. So here's probably where all of our different list elements are coming from. So it's gone and it's tried to query those in the DOM. Then we scroll down a little further, and what we notice is that basically every single time Jake is selecting a new tab, he's actually going and setting interval on this animation, but he's not clearing it. So that's going to end up causing a leak if we continue doing it. One thing he could do here is probably go and actually, if we scroll down, we can see the fix. If he just went and actually assigned like a variable for that timer, for that interval, we can go and clear it up when we know that it's no longer necessary. Otherwise, we're going to end up with a copy of prepare gallery with everything that comes inside of it, its elements, its function definitions, in memory on every single click. Great, so we've looked at that. Let's move on to another example. Let's go back to the timeline. So Matt Gahn asks, what are scattered objects? So scattered objects are basically something that we mentioned in our docs. You may or may not have come across them before. I'm going to go back to profiles for a moment, clear this stuff up, reload the page very quickly. And I'm going to go and record a heap snapshot. Let's just record a heap snapshot very quickly. And now let's record one after I've clicked the Create Scattered Objects button. Do a comparison between these two. Sorry, I've got to expand this a little bit. Now, one thing that you might run across in your applications is you might have objects that are basically of the same kind, but which happen to be scattered across different parts of your application. So you might be using like the same class in different modules, for example, or across different plugins. Now, one of the nice things about the heap profiler is that it'll actually aggregate all of the different instances for that particular type of item. So in this case, our class is actually just called item. And it'll just aggregate them all into this nice view. So we can go and we can just like drop down and see, OK, well, this is where I have all of the different instances of item. To just give you like a little bit of insight into what the code there is doing, we have two functions here. Both of them are using the item class. This is like a very simple item class. Both of them are using the item class. But in the profiler view, I can actually just get a nice, simple way of drilling down to exactly those instantiations that I'm interested in. Let's take a look at another example. So this is an example from Paul Lewis, it seems. Paul, do you want to come up to read up your email?
No. I've got a feeling you're going to stay beyond it.
I would never do anything like that. Not to an esteemed colleague like you, Paul. You're coming up to do this.
You embarrass me being out of trouble.
Right. So, hi. So this is your section. This is the email that you wrote me up.
That's harsh. Today I walked into the gym and did one push-up in front of everyone, then ripped it off my shirt. Of course I did, why wouldn't I? And I walked out grunting, "You did it, you did it!" Anyway, I'm trying to understand what I see in Heap Snapshots. Help?
I didn't embarrass you in any way.
No, that sounds totally legit.
Not in the slightest.
Do the push-up.
Maybe he'll do a push-up later. Right. So Paul is wondering about how you can find detached nodes in the heap snapshot view. So let's go and create. So let's take a clean snapshot, and then let's take a snapshot after I've clicked on the Create Detached Nodes button. Let's go and record that. Let's go to the comparison view because we want to compare what happened between those two snapshots. Right. And if we go and take a look at HTML div element, what you'll see is that we have a number of elements here which are highlighted in red. If I go and I select one of them, you'll see that we have other nodes that are mentioned in this detached DOM tree lower down in the page, which happen to be in yellow. Now, there's a little bit of a difference between the red nodes and the yellow nodes. So red nodes don't actually have any direct references from JavaScript to them. They're usually alive because they're still part of some detached DOM tree. There might be a node in the tree that's referenced from JavaScript, maybe as a closure or from a variable, but it's coincidentally preventing like the entire DOM tree from being garbage collected. The yellow nodes, so again, those ones that are at the very bottom, do have direct references from JavaScript. So look for those yellow nodes in the same detached DOM tree to locate if you have a leak of some sort. And we can go and we can actually clean that up by clicking on the Clean Detached Nodes button. I'm not going to show you that, but I will give you the demos later on so you can check that out. Eric writes in, and he's asking, how does memory work with V8 hidden classes? So someone told me if the compiler can use hidden classes, your code will execute much faster and will use much less memory. Is this true? OK, so let's try to do that. Let's go and create a new heap snapshot. Let's clear. Let's create a new heap snapshot. Create some objects. Do another recording. So this is taking a while. We're creating a ton of objects here in the background. So it's still collecting and parsing that data and building up the tree. So we go and we take a look here. And what you'll notice is that we have two classes that are of particular interest to us. We have slow purchase and fast purchase. Now I'm going to expand this a little bit so you can see all of the data here. Now, slow purchase has a retained size that is significantly larger than the retained size of fast purchase. If we take a look at our page once again, actually, and I go and do some calculus, which is basically just performing the same operation with those two classes, just one of them is slow and one of them is fast. What you'll see is that fast is actually pretty significantly faster than slow. Let's go and try to explain that a little bit. So V8's optimizing compiler makes a lot of assumptions about your code. It transparently, like in the background, creates hidden classes representing your objects. And using those hidden classes, V8 is able to work a lot faster. If you do things like delete properties, those assumptions are no longer valid, and they can end up causing sort of de-optimizations behind the scenes. So in this particular case, what we see is we have a fast object and a slow object. Functionally speaking, these two classes are very, very similar. The only difference is that in the case of the slow object, I thought I'd be really clever. I thought, maybe the slow object would be faster if I actually deleted a property, right? It's actually using less memory, right? Maybe, I don't know. And so we delete this property from our object. But what actually happens is that causes V8 to actually bail out of doing out of using its hidden classes for optimization, and it makes things significantly slower. Actually, anywhere up to 15 times slower in the case of this particular example. So, although I'm saying try to be careful when using delete, you're almost certain to find it in many popular JavaScript libraries. It certainly has a place in the language. There are valid uses of it, but the main takeaway here is just to avoid modifying the structure of hot objects at runtime. So in this case, what we probably should have done instead of using the delete keyword is just nullifying the object so that it could be properly garbage collected. Because only when the last reference to an object is removed does that object get properly eligible for collection. Great. So let's go and take a look at another example. Before we go on to closures, let's take a look at leaky DOM nodes. So Rob Dobson writes in saying, I suspect that I have an array leak nodes which might be leaking. I'm not quite sure how to find this. Well, the workflow is actually very similar to what we've been doing here before. I'm actually going to once again refresh the page. Normally when you're doing any sort of memory profiling, you probably want to start off with what we call a clean room testing environment. What that means is that you should be working in a brand new user profile without any extensions enabled. Incognito is okay, but there are still extensions that you can end up running there. And your extensions can end up actually impacting your performance scores. So regardless of whether you're doing memory profiling or you're trying to take a look at what's going on with your frame rate, make sure you're generally working in a clean testing environment. So here what we're going to do is we're going to take some heap snapshots. So I'm going to take a snapshot before this action, go and create some nodes, take one right after, take a look at the comparison, and if I scroll down here, let's see if there's anything of interest. So at the very bottom, you can see that we have our detached DOM tree. Now, you're probably going to be doing this on a much larger screen, if you're at work, but it's usually good to actually have DevTools fully open, on a second screen, so you can take a look at all the details here. But if we expand the detached DOM tree here, what you'll notice is that the leak nodes array that Rob was talking about is actually visible here, so it is in fact leaking. You take a look at the sources for what he's doing here, and I'm not sure which example this is. I think it's this one. But he's basically, actually, I've got some slides on this. So this is to do with DOM leaks. So what we have here is a graph that basically talks about a page containing a parent div with the ID tree and a child, like an A-link with the ID leaf. And if we walk through what's happening here, what you'll see is that we're first of all just going and selecting tree, we're selecting leaf, we're selecting body. We're first of all trying to remove a reference to tree. And we're thinking, OK, well, normally you'd imagine that actually cleans up everything. But tree isn't able to get properly garbage collected because tree ref is actually still being referenced up here. And so to fix that, we set tree ref to null. Now, unfortunately, it still can't be correctly garbage collected at that point because there's an indirect reference to tree from leaf ref. So if you see here, we're still trying to reference something that is a part of tree. So you have to also set leafref to null in order for this entire tree to be properly garbage collected. Let's take a quick look at closures before we sort of dive into some more V8 stuff. So Paul asks, how do I analyze the impact of closures on memory? I'm lazy, Ken has explanation or demo. All right. How about I give him an explanation? Right, so closures are pretty powerful. They enable us to sort of use inner functions to retain access to outer function variables, even after sort of the outer function is returned. Unfortunately, closures also happen to be excellent at hiding circular references to JavaScript objects and DOM objects, which can sometimes be something that leads to memory leaks. So if you're using closures, just make sure that you understand what references are retained inside the closure. In this particular case, we have an example. We have sort of three examples of more or less something very similar. But we happen to be using eval in the very last example, and we're passing through an argument to our function in such a way that there's going to be constantly sort of a reference to our large string or anything that is passed as an argument there. That is going to make it very difficult for that to be properly cleaned up. Your inner functions in your closures usually need to be able to access all the variables from the outer functions, meaning that as long as a reference to it exists, variables from the outer function can't be correctly garbage collected. And so they'll continue to consume memory until after those functions have completed invoking, which might lead in memory leaks. So just be careful with closures as well. So we've covered DOM leaks, we've covered closures. Quick tip to do with timers. So timers can also be something that are a little bit tricky to deal with. Anything you're doing repetitively inside a timer can be anything that is left running for quite a long time that you need to be pretty careful with. If you've got something like a slideshow that loops forever, just make sure that nothing in the slideshow itself still maintains references to DOM objects that could accumulate leaks if they happen to be GC'd. I wanted to quickly mention ES6 weak maps. Has anyone here heard of weak maps before or used them? Awesome. Right. So the idea here is that we have basically two ways of defining private member data for a class. So we have two-person classes. They're basically doing the same thing. This is your typical classical example of having a module with private data and public data. So person is a closure that captures some private data. And that private data, so in this example on the left where we see our private data, so you see that var private data, that is basically a strong reference. The garbage collector is only able to collect an object if there are only weak references to it or no reference to it at all. The weak map version of this, so weak maps are basically something that come in ES6. The weak map version holds keys weakly, and that basically means that the person instance and its private data are eligible for garbage collection. When a person object is no longer referenced by the rest of the application. It's basically just a new type that helps us avoid memory leak situations a little bit more easily than we have with ES5. Just an example of where the language is trying to help you, avoid shooting yourself in the foot. So we've walked through some very quick demos. I've got a little bit of a cheat sheet for you. Some people are really stoked whenever they hear that there are cheats available for something, so maybe you'll be excited about that too. So this is the way that I usually approach any sort of memory profiling or performance optimization. Design first, code from the design, and then profile the result. What this is all about is simple designs are usually easier to optimize if you follow this pattern. Sometimes profiling can reveal problems that you don't find when you go and do things like premature optimization. Premature optimization is definitely the root of all evil. Whatever you take away from this talk today, please make sure you're trying to make sure that your code and the solutions to your code make as much sense as possible first before you go and try designing for performance. You can always apply those performance optimizations at the very end. So don't let performance considerations affect the design of a piece of code. That can sometimes result in code that is not as visually pleasing to look at and deal with as is possible because you complicated it with the optimization. So here's my memory checklist. The first thing you need to ask yourself whenever you think you might have a memory issue is my app using too much memory? The timeline memory view and Chrome Task Manager can help you identify if you're using too much memory. Remember that memory view gives you everything from tracking objects that are allocated to live DOM nodes to JavaScript event listeners in the inspected renderer process. Is my app free of memory leaks? Use the Object Allocation Tracker. Object Allocation Tracker can help you narrow down leaks. It looks at sort of the JavaScript object allocation in real time. You can also use the Heap Profiler to take heap snapshots, analyze memory graphs, and compare snapshots to discover what objects are not being cleaned up by garbage collection. How frequently is my app forcing garbage collection? If you're GSUing pretty frequently, you may be allocating too frequently. So use the timeline memory view once again just to help you identify pauses that are of interest. There are some good rules that you can follow. Avoid long-lasting references to DOM elements you no longer need. DOM leaks really suck. They can sometimes be a little bit tricky to discover. But as long as you're keeping an eye on any references you're making to elements, and especially when you're in loops, you're making sure to either nullify those references when you're done, or not make those references in the first place. That's even better. Properties of objects like DOM objects might contain references to other objects or JavaScript objects that contain references to others. That can end up causing circular reference issues that can lead to leaks. V8 is really, really awesome at getting around some of these issues for you, but it's always good to just keep these in mind when you're developing your apps. Better than dereferencing, use local scopes, unbind events that aren't needed anymore, so unbind those event listeners. Be careful when you're storing large chunks of data you're not going to use. So this is particularly important when you're looking at anything like storing data offline, storing data for a temporary user session. Make sure nothing really large gets cached that you don't want to cache. Make sure that your caches don't accumulate forever. And have an aging mechanism to get rid of old objects. Because a lot of the time, you can end up caching large sets of data that the user is never going to need to reuse once again. So just be careful with that stuff. Manage your local cache adequately. So we've been looking at a little bit of DevTools stuff. I'm going to spend a little bit of time talking about the conceptual material of how JavaScript manages memory in V8 to explain some of the stuff that we saw in our demos. For anyone that hasn't quite grokked it yet, why does perf matter? Well, first of all, we care about delivering silky smooth apps. Everyone wants happy users, and silky smooth apps can help us get there. We want longer battery life, smoother interactions. We want our apps to live as long as possible without having to worry about them crashing. Nothing is free. So the fastest page, does anyone know what the fastest page on the web is? Anyone at all? It's about blank. That is the fastest page on the web. Anything that we add on to that page actually ends up making it slower. So nothing is free. Use tools like the Task Manager to keep an eye on what resources you're using, because you're always going to end up paying some price for those resources. If you take a look at this, these are some stats from last year. Google Apps, so things like Gmail, Docs, spend about 50 to 70% of our time in V8. A lot of popular sites spend somewhere between 20 to 40% of their time in V8 on JavaScript execution time. So it's still an area that, if you end up having leaks, is worth actually optimizing on. As Nat sort of covered in his talk, most of the time we're trying to hit 60 frames a second in our apps to deliver on those smooth experiences. And that basically gives us 16 milliseconds to get everything done in. So for Chrome's workload, we're looking at 16 milliseconds for dealing with loading data, parsing HTML, dealing with the layout of the page, JavaScript execution. Anything that ends up slowing that down is going to result in your user seeing pauses and jitter. And that's going to basically mean them seeing jank, right? So jank manifests itself when you blow your frame budget. If you aren't able to complete within that time, you're going to end up missing your frame, and your animations are going to end up seeming sort of janky. So visually slow to your users. We don't want that. Blow your memory completely, and you're going to end up seeing the "he's dead Jim" message, the friendliest message ever, which basically means that the operating system has terminated your tab because it's run out of memory. Again, something that we don't want to happen, and we can prevent by avoiding memory leaks. Whenever it comes to sort of the performance versus versus memory battle, where we've always got sort of one side that says, you can always throw more memory at a problem. I don't need to worry about memory leaks because I'm just going to add, another 16 gigs of memory to my system, right? But unfortunately, the reality is that, this isn't a problem that can just be solved by throwing more memory at it. You think about like your grandma that maybe has a Chromebook, and maybe that only has like 4 gigs of memory on it, or 8 gigs, or whatever it is these days. That has significantly less than your development system at work that has like 32 or 64 gigs of memory, or whatever it is you crazy kids have today. But whenever it comes down to the old age performance versus memory trade-off, opt for performance. Let's try to get it great for everybody. So let's take a look at some memory management basics, right? So here's what we're going to be looking at. We're going to look at the types of values that there are, how values are organized in memory, what is garbage, and actually define properly what is a leak. So JavaScript variables can be 4 primary types. We have Boolean, number, string, and objects. So the Boolean type is really just true or false. You guys already know that. Number type is basically any double precision floating number. You've got the string, which is like a UTF-16 encoded character array. Then you've got your objects, which are like a key value map, right? So those are the 4 primitive types. Objects are built around key value mapping. The key goes into the square brackets, and this is always a string. Unless you're talking about like ES6 maps, which allow you to have non-string keys, but we're not going to talk about that. No matter what you put into to sort of those brackets, it's going to end up being coerced into a string. And then you use that as sort of a lookup table. And then for that value, you can store basically any JavaScript object inside of that value. So think of memory as a graph. The memory graph is a pretty fundamental concept when it comes to trying to understand how browsers handle JavaScript performance. So think of memory as a graph with primitive types. So those numbers, those strings, those objects we were talking about, it could visually be represented as a graph with sort of a number of interconnected points that look a little bit like this. So we're looking at sort of a whole bunch of circles here and lines on this side. But let's start from the left of the blue circle here. So the root node. This is the root object that's inside the memory management system. It's not something you can explicitly sort of manipulate or do anything crazy with. But this is just where every object that you create descends from. And it's also called the root. From that root, it references global variables. The red objects here are object variables. So those can reference other variables. And the green circles are scalar variables, like a Boolean or a number, and that can't really reference anything else. And you can see the green node at the very end here. I'm not sure if my cursor is visible. That green node at the end here is just at the upper part of the screen is basically the terminating node in this part of the object graph. So objects have a concept of a retaining tree. This is the paths sort of along the graph that are keeping the object from being classified as memory. So on this side right now, you can see that we have a green node over here in the center. Let's look at its retaining tree for this green node. So the retaining tree for this green node is this yellow node right here, the root node, as well as this other path from the root to the other yellow node. And the other actually has 2 paths to it that are keeping it pinned in memory. If both of those paths are terminated, then the object becomes garbage collected, and it's eventually correctly collected up. So what about removing a value from that graph? Well, this is a fairly basic operation, but it's sort of important to understand how you can remove a value from a graph. So if we want to remove the red value, so this value at the very end right here, if we want to remove that from the graph, we could cut this edge right here from the root node to the first green node, and then the red value becomes garbage. If we cut this edge, it's also garbage, or we cut this edge. Basically, any of these edges cut would make the red node garbage. And that brings us on to that question of what exactly is garbage, right? Well, it's all values that can't be reached from the root node. Or if we say it another way, it's all values that are lacking any sort of retaining path in this system. So if something doesn't have a retaining path, then it becomes garbage like these nodes that you see right here. So you'll see that here, there's no path from the root node to these values. These values are properly garbage collected. What about garbage collection? At the next garbage collection process for these nodes that we're talking about, they're going to be cleaned up. And that brings us to trying to explain what garbage collection is all about. The first step in garbage collection is to find all of the live values in the system. The second is to return the memory used by the dead values back to the system so that they can be recycled later on, as we see here, right? And there they go. What about a value's retained size? So another property that basically every value inside of JavaScript has is its retained size. So the retained size you could probably conceptually think about as sort of the amount of memory that would be freed if the value went and became garbage. And if so, that's the size of the value and its descendants which sort of lack retaining paths. And so if we look at the yellow node on this graph, its retained size of this new yellow node is both of the green node size plus itself. And if we go all the way back sort of to the root node, the retained size is all of the memory that's being used by your JavaScript. Which takes us on to what is actually a memory leak. Well, a memory leak is something that's existed in basically any sort of computer system ever created. But the idea is that it's a gradual loss of the available system memory. It occurs when you've mistakenly left a retaining path to some value inside of that graph that we were talking about. So JavaScript web apps can usually suffer from similar memory-related issues that you'll see in native apps, mobile apps, Android apps. Leaks to do with bloat, but also to do with garbage collection pauses. So you might think that the value has no path here. So a value that erroneously still has a retaining path is something we need to be concerned about. So you might think that the value has no path, starting from the root node, getting to it, and that'll be collected on the next round of garbage collection. But you'll occasionally end up accidentally leaving a retaining path. And so you end up with the situation of having a memory leak. So if we take a look at this really simple example, it's a little bit Gmail themed, where we've got sort of this email message and we're basically appending it to a list. So we have an email object, we have this message field inside of it. We assign that to a div node in the DOM, and we then want to display these email messages. So we add that div node into a display list as well, right? So this is what the object graph looks like after running this code. So that's a very simplistic piece of code. This is what the object graph looks like for it. Somewhere starting at the root node, there's paths to both email and display. And then off to email, there's a path to message. And there's this special kind of edge from the message to the div node. And this is pinning a native object. So I'm trying to highlight that there. That's pinning a native object, an external object that's not directly related to JavaScript, but it just looks the way it does. So maybe the programmer, is trying to go and clean up this list of messages, and they'll do something like, display.remove all children, and you think, okay, maybe all of these divs are gone. Maybe we don't have to worry about this problem anymore. But whoops, something has gone wrong. We've actually managed to cache a reference from the message object to the div node. And so until the email itself is removed from the system, which could take forever, we don't know when that's actually going to happen. The div node is going to be pinned to memory, and we've leaked it. Imagine this happening on a system of great scale where you could have hundreds of messages being loaded at the same time. It could easily escalate to a point where you're leaking so much memory that you're not able to create new tabs, or your current tab ends up crashing. So some memory management basics that we've covered. In general, the basic idea is that memory management in JavaScript and all the values are organized inside a graph. So remember the graph. They can have retaining paths. Any value that lacks a retaining path becomes garbage. And then there's retained sizes. And that's sort of the amount of memory that you're going to free up when the value itself becomes garbage. Let's go from sort of the general to the specific and talk about the way that V8 manages memory and what happens during a GC pause. We're then going to talk a little bit more about DevTools and just summarize some of the tools that are going to be useful for you in your day-to-day workflow. So the first question you usually ask yourself is, what is the cost of actually allocating memory in JavaScript? And surprisingly, it's not the call to new. So going and creating a new instance of a class, it's actually not that. Typically, the call to new is actually pretty fast. It's gotten much faster in recent years. It's really fast until you've gone and you've exhausted your entire memory pool. And we'll get to this in a moment of what's actually happening. But at that point, the runtime is forced to go and do a garbage collection. And this is where all the time is spent. It can actually take milliseconds. So remember, if you're trying to write a 60 FIPS app and you've only got 16 milliseconds to do everything in, a garbage collection pause might pause your application for 5, maybe 10 milliseconds, which for Gmail might be okay, but for some apps it's really too long. As Nat mentioned, GC pauses have become less of an issue in recent years. But again, it's just something that's useful to be aware of. So the next thing we're going to cover is the young generation and old generation concepts in V8. So V8 manages memory in 2 generations. There's the young and there's the old. The young generation will probably be telling you get to the chopper. The old generation will be telling you get to the walker. That's terrible. I'm sorry. I apologize. That's the only terrible joke I'm making today. Right. By young and old, what do I actually mean? Well, by young and old, I mean how long has the JavaScript value existed for in this system. And over time, sort of young values end up getting promoted to old values. So after a few garbage collections, if the value of an object survives, meaning there's a retaining path, and it's kept in memory, eventually that value ends up getting promoted to the old generation. So as you can see, young values end up getting translated into old values over time. So what are the properties of the young generation in V8? Well, it offers really fast allocation. So young Arnie, really fast allocation. It's frequently collected. In fact, if you're using the DevTools timeline, you can usually see the GC event on it. So if you hover over one of those bars in the timeline, you can actually see the GC events and dive down and see some more information. That'll give you some insights that can be useful. So those will give you some hints on young generation collection. Then we've got sort of the old generation. In contrast, it offers fast allocation, but the collection is usually a lot slower. The good thing is that it's really infrequently collected, and some of the old generation's collection occurs in parallel with your page's execution. So whereas like the young generation is really just everything is stopped, your collection occurs, then your page resumes, the old generation mixes a little bit of collection with your page's execution. I'm mostly going to be focusing on the young generation here because that's where you're going to feel the pain inside your apps. And it's going to happen pretty regularly. So let's try to cover it. So it's important to understand why collecting the young generation is a little bit faster. Intuitively, you usually have to end up understanding that the cost of the GC pause is actually proportional to the number of live objects that you have in memory. Because objects get split into the young generation and the old generation, the young generation actually doesn't survive very long. So after a round of garbage collection is run, most of the values in the young generation don't actually make it. They have no retaining path because they were just used briefly, so they're short-lived objects. They don't exist anymore. And they're not really in the graph. Whereas by their nature, objects in the old generation have usually survived quite a long time. So you can't expect that when a collection is triggered for the old generation that many of them are going to disappear. They're going to be around for quite some time. So knowing the cost of the garbage collection pause really comes down to the number of live objects. And it becomes quite clear why collecting the young generation is so much faster. So let's take a look at the young generation in action. So here, the young generation is split into 2 semi-spaces. There's the to space and the from space. Now the to space is where values that you allocate from your page get executed, like the new foo. It's coming out of the to space, and the from space actually just sits there, not really being used until much later on. We'll see what happens with it in just a second. So assuming that the to space started off empty, and your page starts allocating objects. So let's say that we're allocating objects. We're going to name them something simple like A, B, C, D. Let's look at the allocation. So we go and we allocate A, and then B, and then C, and finally D. And everything up until this point has been really, really fast, and there's been no interruption to your page's execution. But then your page goes and it calls new E. And actually, it's just too big. It doesn't fit into the to space. We've hit a threshold in our system where we've moved incrementally closer to this GC pause, and now we've actually triggered it. So we've got a pause inside of our app. So what happens is that new E doesn't happen. It's kind of paused. So we're still in this state where we just have A, B, C, and D inside of our to space, and the page is paused. Everything halts, and the collection is then triggered. So the first step in a young generation collection is that the from and the to spaces get swapped. the labels to them get flipped internally, and the live value is then found. I'm not going to go into too much detail about sort of this part of the system, but everything that still has a retaining path on the graph is discovered and then marked for copy at this point. So you can see here that A and C are marked, and B and D have not been marked, so they're garbage. They're not going anywhere, and this is most of where our time ends up going. It's where the live values end up being copied from the from space to the to space. So here we are. We've done the copy, we've done the collection, we've just copied the live objects from one semi-space to the next. And there's no other work to be done at this point. It's just ready for the next time there's a garbage collection round that needs to happen. And at this point, your page is resumed, and the object E is allocated, so it's then able to actually do something. So, quick summary, what you have to understand is that each allocation in V8 moves you closer to a collection, so a garbage collection round. The trade-off we talked about earlier between sort of more memory and performance, you start to see why that doesn't quite hold up inside JavaScript, because the more memory you use, the faster you're going to get to this actual pause. And that's actually where you're going to end up losing performance. So just try to take some care there. Not only that, but the more memory you're using, the longer that pause is going to take. And the larger the heap, the longer the collection is going to take to actually occur. So remember, triggering a collection pauses your application. So when the collection occurs, your app gets paused, you get higher latency. Let's say the user is going and clicking inside the application. Well, that click isn't going to register for a while because we've got to do this big collection. So this leads to drop frames per interaction, and in general, unhappy users. And unhappy users are going to end up going somewhere else, and you don't want that. So let's take a quick summary of some of the performance tools that we have available to us. So what the Performance Memory API does is it gives us a great tool for doing in-the-field measurements. So it gives you back sort of three values. It tells you the JS heap size limit, which is the total amount of memory available for JavaScript. It tells you the total JS heap size, which is the amount of memory that's been allocated so far, including the free space. So this is sort of including memory that has already been garbage collected. So you could predict like the I'm dead Jim message by seeing when total JS heap size hits the JS heap size limit. And as the JS heap size starts to get closer and closer, you know that at some point you're going to trigger this and end up out of memory. And finally, it gives you the use.js heap size. And that basically tells you the amount of memory that's currently being used by live objects in the graph. So let's quickly summarize some of the stuff that we learned today in Chrome DevTools, and hopefully this is going to be stuff that's going to be useful to you in your day-to-day jobs. So DevTools memory timeline, we showed it earlier in the talk, shows you everything from parsed JavaScript to calculated styles, garbage collection pauses. In the frames view, it'll show you everything from sort of paint to composite. We're mostly interested in the memory side of things, so it'll show you total allocated memory, live DOM nodes, number of event listeners. Don't forget that you can force GC from the DevTools using the trash icon. That's like a really important step people always miss. This is something we automatically do for you if you're happening to use one of the profilers. In Timeline, it can be useful to force a GC too. Memory distribution, heap snapshots are really useful for that. So once you've confirmed that a problem exists, go and try taking some heap snapshots and dive into sort of the more the nitty-gritty of what's going on inside your application. We let you switch between a number of different views of the data that's available. So we've got sort of three views. We've got summary, which groups by constructor name, comparison, which I use a lot, which compares two different snapshots together, containment view, which gives you sort of a bird's eye view of the object structure. Don't forget the difference between these two colors. So yellow objects have JavaScript references on them. Red are detached nodes. They're referenced from one with a yellow background. Reading results, sort of the DevTools docs cover this stuff pretty well. We're running out of time. So distance is the distance from your GC root. You've got retained memory, which is memory used by all of your objects. The objects they're referencing as well. Use it to know where you're using most of your memory. You've got shallow size, which even small objects inside your application can hold large amounts of memory indirectly by preventing other objects from being disposed. So just keep an eye on shallow sizes. You've got constructors, so we try to group all the objects in the retaining tree by their type. So keep an eye on those. The retaining tree shows you information that will help you understand why objects aren't being collected. Quick tip: if you happen to be using closures, please try to name them, because those will actually show up in the heap profiler, and it'll be really easy for you to go and detect them. So in this case, we've got two examples where at the top, I know this is a little bit hard to see. At the top, we're basically saying var lc equals function, which is not a named function. In the bottom, we're saying var lc equals function lc, which is a named function. The second one will show up as a labeled thing inside the heap snapshot, so you can easily stay on top of that. Profiling memory leaks. Some of you may be familiar with the 3 snapshot technique, which we've had in the DevTools docs for a few years. We've recently retired that technique. The basic idea there was that you started from a steady state and then performed a number of different snapshots and compared what happened between those snapshots to understand whether or not you had a leak. What we replaced that with over time, sorry I'm just skipping through this because of time, but what we replaced that with is the object allocation tracker I was showing you earlier on. Basic idea with the object allocation tracker is that we give you a way to avoid having to repetitively take snapshots yourself to find out if you have a leak. So the allocation snapshots can be recorded from sort of the record heap allocation section of profiles. It combines the detailed snapshot information that you see in the heap profiler with sort of the incremental updating and real-time view that you get inside the timeline panel. It's really useful to use, and I definitely check that out. You can read more about sort of the tracker inside of our docs. Remember that blue bars mean memory allocations. Taller means more memory being used. Gray bars means that something has been deallocated. You can trim down by time. You can take a look at the heap contents quite easily to dig into more information. Very quickly, I'm going to start wrapping up. Something new that we introduced in the Canary DevTools is allocation stack traces. This is a brand new concept. We haven't talked about it before. But the basic idea here is that you can go and you can enable this in settings in the Canary DevTools under record heap allocation stack traces. And it just makes the profiler collect stack traces when you're going and recording your heap allocations. So once you've gone and you've recorded a profile, you'll see that we actually give you a new tab next to the retainers view. And the stack trace is going to be missing from any objects, but if it happens, it just means that it was created by V8 internals. And it just gives you some more information that you can use during debugging. I'm going to gloss over very quickly flame charts. How many people here have heard of flame charts before? Right, so half of you have heard of flame charts. If you're trying to visualize JavaScript execution over time, flame charts are really useful. You would go and trigger them by recording a new CPU profile. If you go and try to select the chart view inside of that, what that'll basically give you is this really gorgeous view that provides a visual representation of your JavaScript processing over time. You can actually dig down to individual functions and see how much time they took up. And by analyzing and understanding your call progression, you can visually gain a better understanding of the execution within parts of your app. So the height of these actual bars isn't really significant. They just represent function calls which occurred. What is important is the width of those bars. You can take a look at more of this stuff in our docs. Is optimization actually worth the effort? I'd actually say yes, I think it is. I know that I've been throwing a lot of stuff at you guys today. There's been a lot of stuff on tooling, a lot of stuff on V8. This stuff is actually worth knowing about. This is a graph from Gmail's memory usage that we took over a 10-month period using the performance memory API. And what we discovered, if you take a look at the very left, is that you see that memory was actually really out of control at one point. The green line is the median, and the blue line corresponds to the 99th percentile. And you can see that for our power users, using the tools that I showed you today, we were actually able to reduce memory footprint by up to 80%, if not more. And for our average users, we were actually able to reduce memory footprint by 50%, which is kind of huge. So for long-life applications like Gmail, being able to narrow down memory leaks, being able to squash them down is actually a big deal. If you do end up having memory leaks in your applications, I hope that you'll take a look at our docs, you'll learn the tools, try to use them on your own apps. There are a bunch of resources I'm going to link you up to later. There are some good case studies that have been done by everyone from Imager to Drupal to Strong Loop to other people who've been looking at memory leaks in JavaScript and how they apply to everyday apps. Last thing to remember, ask yourself these questions if you think you have issues with your app's memory. How much memory is your page using? Is your page leak-free? How frequently are you GCing? Know your arsenal. Make sure that you sort of know the profiling tools inside of things like Chrome, regardless of whether it's, also looking at the Firefox DevTools and other DevTools that are out there. So know your arsenal. Hopefully, at least one or two people in this room are excited about the idea of having a better grip on memory profiling. Maybe some of you are just excited that this talk is over and you get to actually eat. But overall, I hope that you at least got something out of this talk. That's it from me. Thank you.